session, and I'll have only this one, and then you will not see me again. Yesterday we talked about data and then use of data in 1D, 2D, 3D models, where the accent was, the focus was on model calibration, preparation of models for some potential future use. And since I had those, since I had those questions before, I go, okay, fine, you do measurements, you do your model calibration, etc. What's the use of that? What can you do with those models? So that's why I prepared a few short samples of examples of practical use of 1, 2, 3D models. Once they are calibrated, verified, we are sure that they are giving pretty much reasonable results. So that's what this morning thing is about. One example, one of practical things that come out from sediment flow and sediment transport and bed evolution models is the long-term changes of bed in the river or rivers, long-term bed evolution. And for that, because sediment processes are very slow, for that we need long-term simulations, and it's the typical request is also large-scale simulations. So I'm giving here an example of such case: one big river, 2 large tributaries. Large scale means, see, we have over 300 kilometers of the main river, main water course, over 100 kilometers of one tributary, the downstream tributary, as I call it, this one, over 60 kilometers of upstream tributary, altogether almost 500 kilometers of flow. We were asked to look at the long-term, 15 years morphological changes, and for that you can use nothing but 1D model. Everything else, 2D, 3D, is simply too slow to simulate something like this. I'm calling this major water course, one tributary, the other tributary, whatever, because this is done in combination of 2 projects. One project is our National Science Foundation, and the other is our hydropower authorities here in the country. So one part of this, which belongs to hydropower, is kind of still, we have obligation not to publish all the results, etc. So I'm calling it one river, one tributary, etc. But essentially, this is Danube, this is Sava, this is Tisa River. Go ahead. We were simulating, as I said, 15 years of said reservoir simulation. That's actually in the domain of Iron Gates 1 reservoir. We were simulating 15 years of life of that reservoir's long-term sedimentation, starting from the year 92 to 2006. I cannot show all 15 years on a graph, apparently, obviously, because it would be so much on one slide. So I'm showing 1 year. It's the last year of simulation, 2006. That's especially interesting because 2006 was, if you remember, both here and in Hungary was one of highest discharges that happened. It's about 16,000 cubic meters per second in the downstream part of the Danube, which is close to one in 100 years, if there are hydrologists around here, once in 100 years event. There's a huge, since we were using hours for time scale, this is, this 15 years amount to about 130 something hours. The last year, the 2006 had some time in the spring, in April or so, had a peak. And you can see, for example, here, comparison between our model and data that come from Hydromet services. It's the upstream end of the main water course, which is Danube around Novi Sad. You see peak values, 79 over 79 meters above sea level, and the wave pretty much preserves the same shape as it travels downstream. Go to the next one. This is in Tisa, elevations in Tisa River, around the mouth, the confluence with the Danube. The peak is somewhat lower, but since it's at the mouth, it's pretty much the same as in Danube. The next one shows Danube further downstream, Zemun, which is upstream from Sava mouth, from confluence with the Sava River. Again, peak is lower, of course. Go ahead. Belgrade, Sava, Belgrade mouth, close to what we have in Zemun. It's the same area, so it influences each other. Go ahead. This is further downstream in Smederevo, which is about 50, 60 kilometers downstream from Belgrade. This is discharge now, so they have discharge measurements, Hydromet services, so we compare discharges. You can see that our computations show up and down zigzagging here as opposite to measurements. That's because this unsteady flow in a Danube is governed by two sides. One side is upstream side, that's natural waves, flood waves that come into our system. And the other end is hydropower plant at the downstream end, which opens and closes and produces very frequent changes in discharge and free surface elevation. That's the regime of hydropower plant. We have some data that come from hydropower plant, frequency of 1 hour, every hour measurements. And we have a combination of those data with data that come from Hydromet services. They have daily values, daily elevations or daily discharges. So at Smederevo, we're getting close to the downstream end, to the hydropower plant. That's why data that we are showing here are kind of smooth, because those are daily values. But our model is feeling the influence of downstream and of downstream condition of hydropower plant at that point where discharges go up and down frequently within 1 hour. Go ahead. When we come closer to the dam, this is Donji Milanovac station, then you can see those changes clearly. I cannot show on this scale. I cannot show more than let's say 3 months, which I'm showing here. That's something that shows clearly what's going on. Everything. If I try to put 1 year here, then it would be a big mess of zigzag. Nothing could be seen. So these are free surface elevations measured measured each hour, and our computations are showing hourly values. By the way, we had to use, to cover those changes that are imposed by hydropower plant. Every hour change, we had to use 15 minutes time step in our computations. So that fact by itself shows that the extent of the model. We have to simulate full 1D unsteady flow equations, 15 years period with the time step of 15 minutes. Once we have a model calibrated, ready, etc., I'm showing here is that with the model we can really follow actual flat wave traveling downstream the system. And we did that not only for 2006, but the whole period, 92 to 2006. We included sediment in it, and then the final result is morphological changes in our system. Essentially changes here, we'll see in a second, change is represented as a change in a cross-section area. So if we have erosion at certain cross-section, then we have enlargement of a cross-sectional area. If we have deposition, then our cross-sectional area shrinks, and all those changes are eventually having influence on flow, discharges, free surface elevations, most of all. Go ahead. They have a program that follows the life of hydropower plant reservoir over more than 30 years. They have measurements of cross-sections every 5 years, 5, 6 years or so within that period. And from those measurements, we can extract changes in free surface elevations. We can see whether one cross-section was eroded within a large cross-section area, or whether there was deposition, sedimentation in the cross-section, so the cross-section shrinks. These are results of measurements between 89 2006, not exactly same what we were computing, but close. We were modeling 92 to 2006 because that's when we had data, especially for boundary conditions. Downstream end of the reservoir, this is close to the dam. We have about 50, 60 kilometers of massive deposition. And then upstream, there is intermittent deposition erosion, which, when we simulate it, looks like this. We cannot expect exact agreements, but we did recover massive deposition with the model in the same area close to the dam, and again, upstream end with the intermittent deposition and erosion. Order of magnitude is similar. Go ahead. This is the upstream end of the reservoir on the Danube River. Now there is a little more disagreement in the data and the simulation period. It goes from 88 to 2005. Now our simulation period is 92 to 2000 to 2006. So our simulations are recovering again, similar trends and similar order of magnitude. On tributaries, on Sava River, there is far more morphological changes, far intensive morphological changes as compared to Danube. Similar situation with our simulations, and on Tisa also small changes, similar order of magnitude of changes that the model recovered. So that's typical use of 1D model, which we can use for long-term, large-scale simulations, and we can recover what's of most interest in those situations, long-term morphological changes in the watercourse. Another example is evaluation of river bend stabilization measures. We have a river bend that sometimes is unstable, eroding one bank, depositing depositing on the other bank of the river bed, etc. That was the case here. We had as measures for river bed stabilization, we have two proposed measures with two sets of submerged weirs used as river training structures. This calls, because the structures are submerged, that calls for 3D model, because if the flow goes over the structure, submerged structures, then we have significant vertical velocity component. The goal of those measures was to either stop the process that's found there, eroding one bend, one side of the river, the outer bend, and depositing on the inner side. If we can stop it or reverse the process with our structures, we put the structures, you can see, since those are submerged weirs, we put our grid tents around those structures. And those were, next one, this was one set of structures. This is the bend. You can see it because we see the bed elevation here. Previous one. We can see the bed elevation here. We can see that the main flow goes, this is the direction of the flow. This is the upstream, downstream end. You can see the main flow goes over this side of the bend. This is erosion here. This is the position on the other side. We tried this combination of submerged weirs. That was one version. The other version was this one, a bit more of them concentrated immediately upstream the bend. And model went through the same process as what we were showing yesterday. Calibration, verification, etc. Once we were without, of course, structures. And once we were satisfied with the model results, then we introduced structures into the model. And the final result is morphological changes of the bed, cumulative erosion deposition. This was done for a period of something like 5 days. Simulation, once you put structure, then the flow starts. This is completely different situation now compared to what we had before without structures. Once we put structure inside, the flow starts working on sediment, eroding sediment in some places, depositing somewhere else. I think that the next one, those are the results for the first one. It's more visible for the second set of structures. You see those streaks, first the scale. Scale says that yellow and then brown and red is deposition, and then greenish and dark green, etc. is erosion. What's happening when you put the submerged weir on the bottom? Flow goes over the submerged weir, accelerates, and then erodes immediately downstream from the weir, that produces erosion. Material that's eroded is depositing again further downstream. So those streaks here, so greenish, show the location of weirs. There is erosion upstream, downstream from the weir, and then further downstream deposition. Again, erosion at the weir, immediately downstream, and then further downstream deposition. And what we see is that this whole area with weirs here keeps the sediment, slows down the flow, and sends it the other way, and then we have areas of erosion along the inner side of the bend, and that's what essentially was the goal. And if we put the back previous one, we see that the second set is actually doing the better job. Of course, there are numbers behind this, since we can, for each part of the model, for each sector, typically there is something that's called evaluation sector, that they want to see what's going on when we put those things in flow. We can compute the bed elevation, we can have a bed elevation before structures, and then we have bed elevation after the structures are in, and after a certain period that erosion and deposition work, and we can subtract those, and we can see the amounts of sediment eroded or deposited at different sections of the model. Another example, and the last one for today, is evaluation of proposed river habitat restoration measures. We have a river that's practically channelized with river training works, and that is not the natural habitat anymore. It's practically channel, which does not whatever lives in that river, or used to live in that river, things like fish and crustaceans and other living creatures in the river they don't like a channel type, they like a river environment which has intermittent deep shallow areas, etc. And goal was to try to recover that in this channelized river. Proposed measures, again, that came from designers were river widening, which is, here river was slightly widening on this side. Rootless dikes, existing dikes were cut off the bank, that's why they call it rootless. And structures of this type, called chevron dikes, which are horseshoe-shaped structures submerged. The major thing is here that they're submerged, and we were trying to compare, see the effects of all these measures, having in mind the major goal that we have to kind of recover that intermittent deep and shallow areas in now, at that point, channelized river. And go ahead. Again, goes model calibration, verification, etc. Let's see what's the influence of those measures to bed elevation changes. This is cumulative erosion deposition after, again, 5 or so years of simulation with 3D model. This, we don't see much from this thing. This is the location of chevron dike. We can see that there is some kind of erosion here and deposition down there. What's actually happening is that because that chevron dike is again as a horseshoe shaped, flow comes from the upstream side, goes because it's submerged, goes over the pier, digs the hole inside, immediately inside the chevron dike, and then deposits that sediment further downstream. From this, we cannot see it clearly as in previous case, so I'm adding some further figures that show, actually support what I was just saying. We did the time history analysis of what's happening, what's the influence of those 3 measures, especially the chevron dike. We had, this was a part, it's called submodel because it's a part of a larger model. We had the model without modifications, without putting any of those measures in it. We have a model with combined widening and rootless dikes and its results, and we had a model with combination of the previous 2 measures and that chevron dike. And we were looking at the computational point that's inside the chevron, right immediately at the upstream end of the chevron, And then we had a computational point that's about 10 meters further downstream, and let's see the results. This is for the point that's immediately inside the chevron dike. Results are given, this is a cumulative bed elevation change. Results are given for the original situation without any of those modifications, for first set of modifications, widening and dikes, and then for combination of those two with the chevron. We can see that the first widening and rootless dike don't produce any effects. When we put the chevron in, then in that point immediately inside the chevron, there is significant erosion. That's that green thing from the previous slide, which goes up to 1.5 meters. You saw that that area is relatively small, but it's fairly intensive erosion, and it shows that it slowly approaches, it will in the future approach some kind of equilibrium. And if we look at the point which is 10 meters downstream, we can see that, again, comparing original situation with those two measures, river widening, rootless dikes, there is no change in bed elevation. But if we add chevron, material that was eroded at the point 10 meters upstream is now deposited at this point. If we look at the previous picture over there, we see that actually deposition area is larger, far larger than the erosion area, but the deposited amount is like half of what was the depth of the hole that was dug in upstream point. So eventual outcome is recommendation of system of chevron dikes as a measure for the river habitat restoration. So those are examples of practical use of those models, and they show that eventually we can give decision makers pretty good specific results. If you want to apply this, then the result will be this. If you want to apply this measure, then, or this measure will not have effect, this other measure will have effect, and even attached numbers with what one of those or each of those measures will do. That was, we have far more examples of things that we were doing, but that shows, that answers the question, why are you doing it? Why are you putting all those models? Do they have any practical use? That's what I wanted to show you this morning.